Welcome to this explainer. Today, we are going to dive right in and unlock one of the most fundamental, fascinating mysteries in all of computer science. How do machines actually reason? You know, we hear about artificial intelligence absolutely everywhere right now, but beneath all the flashy applications and the chatbots, how does a line of code logically deduce a safe path forward when it's placed in a dangerous, unknown environment? Well, by the end of our time together today, you are going to understand the exact textbook mechanics of artificial reasoning. Here's our roadmap for the journey. First, we'll cover knowledge-based agents. Second, we'll say, welcome to Wumpus World. Third, we'll look at encoding the logic. And finally, we'll do a step-by-step walkthrough. Okay, let's dive straight into part one, knowledge-based agents explained. Think about how we navigate the world for a second. Humans can know things, and we can reason. We store information in our brains, and then we use it to solve problems or piece together new knowledge, right? For artificial agents to actually achieve successful behaviors, especially in what we call partially observable environments, where they simply can't see the whole board at once, they need a very similar capability. A knowledge-based agent goes way beyond just reacting blindly to whatever is right in front of it. It maintains an internal state, and it's basically composed of two main parts. A knowledge base, which is essentially a set of logical sentences representing facts about the world, and an inference system, which applies strict logical rules to derive brand new sentences from the old ones. Now, to make this actually work in practice, the agent operates in this continuous, incredibly elegant three-step loop. First, it has to tell the knowledge base what it perceives from its environment. This is how it absorbs new experiences. Second, it asks the knowledge base what action it should take next, which prompts that inference system we just talked about to deduce the best move based on this newly updated reality. And third, it simply performs the chosen action. Tell, ask, perform. It's just a constant, ongoing dialogue between the agent sensors and its internal logic engine. Moving on to part two. Welcome to Wumpus World. So, how do computer scientists actually test this loop? Well, we drop the agent into a dark, scary cave. Welcome to the classic Wumpus World. Take a look at the grid we have here. This is a legendary textbook environment. The agent, our brave little explorer, always starts down in the bottom left corner at square 1-1. Now, the cave is partially observable, meaning the agent can only see the specific square it's currently standing in. The ultimate task? Navigate this grid, find the gold, and return home alive. But there's a catch, of course. There are lethal obstacles, bottomless pits, and a terrible monster called the Wumpus. Step on a pit or walk into the square with the Wumpus, and the game is immediately over. Since the agent can't see the dangers ahead of time, it relies entirely on its perception in its current square. And the physics of this cave are incredibly strict. If the agent is in a square directly next to the Wumpus, it will perceive a stench. If it's next to a pit, it's going to perceive a breeze. And the gold itself, well, that could be completely surrounded by these dangers. The agent absolutely must use these environmental clues, the stenches and the breezes, to logically deduce which adjacent squares are safe to step into and which ones mean certain doom. All right, part three, encoding the logic. Now, an artificial agent doesn't actually smell a monster or feel a breeze on its face, right? So we have to translate those physical rules into mathematical propositional logic, and this brilliantly illustrates exactly how that translation happens. Look at how we take a plain English sentence like pits cause breezes in adjacent squares and encode it for the machine. If we use the letter B for breeze and P for pit, we can write a logical sentence for our starting square 1-1. B11 happens if and only if there is a pit in 1-2 or a pit in 2-1. Boom. The machine now has a mathematical representation of the cave's physics. A breeze in that square unequivocally means a pit is in one of the direct neighbors. The entire knowledge base is really just a massive conjunction of all these logical sentences combined together. And finally, part four, our step-by-step walkthrough. Let's actually watch this build into real reasoning as the agent navigates. Our agent starts at square 1-1. It knows for a fact there is no pit there, which we label as rule R1, not P11. It also knows the general rules of the cave we just talked about, like R2 and R3, stating that a square is breezy if and only if a neighboring square has a pit. Okay, so the agent takes its very first actions and records its perceptions. In square 1-1, there's no breeze. That becomes a new fact, R4, not B11. The agent then moves over to square 2-1, and suddenly, it feels a breeze. It tells its knowledge base, R5, B21 is true. Based on just these 5 sentences, the agent must now ask its inference engine, where exactly is the pit? Now, what's really, really interesting is how the agent actually goes about answering that question. It uses a brute force logic technique called truth table model checking. The agent looks at all the relevant proposition symbols. Right now, there are 7 of them in play regarding the immediate surrounding squares, things like B11, P12, P22, and so on. Since every single one of those symbols can be either true or false, there are 2 to the power of 7, or 128 possible models. A model is just a hypothetical version of reality. The agent literally has to evaluate all 128 possible versions of the universe to figure out which one it's actually standing in. Here's a snapshot of what that truth table looks like. The agent methodically lists out rows representing every single combination of true and false for those 7 variables. Now, obviously, most of these models describe realities that totally contradict the agent's known facts. For example, any row where B11 is listed as true is immediately thrown out as a false model because the agent already perceived with its own sensors that there is no breeze in square 11. So, the absolute crucial point here is filtering down this massive table. The agent's goal is to find the models where the entire knowledge base evaluates to true. Look at that column on the far right. Out of all 128 hypothetical realities, only 3 models perfectly align with everything the agent knows to be true. The general rules of the cave, the lack of a breeze at the start, and the terrifying presence of a breeze at square 21. The agent has successfully narrowed reality down to just 3 possibilities. Let's anchor all this math back to the actual physical grid for a second. The agent is currently standing at square 2-1. It has to make its next move. The 2 unknown adjacent squares are 1-2 and 2-2. It desperately needs to know if there's a pit in either of them. So the agent asks 2 specific questions. We call them conclusions to its newly filtered knowledge base. Alpha 1, there is no pit in 1-2, and Alpha 2, there is no pit in 2-2. And guys, here is the climax where the actual reasoning happens. The agent checks Alpha 1 against those 3 surviving reality models. Look closely at the column for P12. In all 3 models where the knowledge base is true, P12 is strictly false. This means in every single possible reality that matches the agent's exact experiences, square 1-2 does not have a pit. The agent has logically, mathematically deduced that square 1-2 is 100% safe. But then, look at alpha 2. In the column for P22, it's false in one model, but it's true in the other 2. Because the knowledge base does not entail alpha 2 across all possible models, the agent logically deduces that square 2-2 is a gamble. It's dangerous. It doesn't guess, it completely knows. Simply by evaluating truth tables, our artificial agent just turned simple environmental clues into a definitive life-saving deduction. But this leaves us with a truly fascinating thought to wrap up on. When you walk into a room and instantly intuit that something is just out of place, is your brain actually just rapidly running a subconscious truth table across hundreds of models? Or is human intuition something fundamentally different from this kind of propositional logic? I really hope this explainer gave you a clear, concrete understanding of how artificial agents perceive, encode, and actually reason their way through complex problems. Keep asking questions, keep evaluating your own models, and keep learning.